This is the pulse that we all want. Laser diodes are current operated devices, and so we use a current source to drive them. What we want is a very fast rise time, a very fast fall time, and a constant current in between. If the pulse that you get instead looks something like this, you're not alone, and you've come to the right place. The issue here is basic electronics, and so let's spend a moment talking about that. This is a symbol for a battery. If I take a battery and connect it to a piece of wire and run a current through that piece of wire, I will get a magnetic field around that wire. We are converting current into a magnetic field. Likewise, if we were to take a loop of wire and connect it to a current meter and take a magnet and push it in and out of that loop of wire, we will generate a current. Faraday knew this, and he came up with Faraday's law, a formula that relates the speed of the magnetic force versus the current. Lenz also worked on this, and he discovered something else. He found out that there is something called self-inductance, which means if we run a current through an inductor and then change that current, the inductor will oppose that change in current. Devices that convert energy into a magnetic field and reverse are called inductors, and the property is called inductance. Inductance is measured in henries, but a henry turns out to be a very large unit. So we deal mostly with millihenries, microhenries, and nanohenries in the business that we're in. This may sound like a very tiny quantity, but in reality it's quite important, as we'll see when we talk about high-speed pulses. There is a formula, and it's the only one we're going to throw at you today, that is extremely important. The amount of voltage that we induce in a circuit is equal to the amount of inductance, L for Lentz, and the speed of the change of the current. In our laser driving business, we may run into dozens or hundreds of amps, so DI is a number in that area. The amount of time it takes to go from 0 to hundreds of amps could end up being nanoseconds, a very small number, so this combination is going to be a very large number. It only takes a few nanohenries of inductance, as you can see, to give us volts of reverse EMF. And we're dealing with laser diodes that only need a couple of volts to operate on, so this ends up being a key item. So why do we care about inductance and talk about laser diodes and interconnections? It's because when we drive an inductor with a pulse that looks like this, what we will actually get is something that looks like this. If you're into control theory, you'll recognize this as a first-order system. We're feeding a step into something that gives us a pulse like this, and so we have now extended the leading edge of our pulse and slowed it down. In addition, we have capacitance in our system. This is caused by any two conductors that are of different potentials that are near each other, and that's called a second-order system. So when we combine inductance and capacitance and drive it with a pulse like this, a step, we end up getting something called ringing. So now we have two problems, a slow leading edge and a diminishing sine wave. Your pulse may not quite look like this. It depends on the amount of damping, in other words, the amount of loss in the system. You may end up with a pulse that looks like this. You may end up with a pulse that has overshoot, and then it settles out. If you have a little less damping, and if you have very little damping, you may have a pulse that rings all the way to the end of the pulse. A laser diode is a very fast device, and it will follow this current. So you will get this kind of light output, which of course is not what you want. Furthermore, at the end of the pulse, we can have another situation happening. We can have ringing at the end of the pulse, and this represents reverse bias on the laser diode, which can damage it. So inductance is not only inconvenient and gives us distorted pulses, it can damage either the laser diode or the pulsar or both. There is one other issue that we have to deal with when we think about this, and that is a current source, like a laser diode driver, has a finite amount of voltage that it can generate. That's called compliance voltage. It's a current source, but the voltage is used to drive the current through the load. And if it turns out that we have a lot of inductance in our system, we may run out of compliance voltage and not even be able to reproduce the pulse, which is why Steve mentioned no pulse or low pulse. We have a lot of things to overcome: the forward voltage drop in the laser diode, the resistance in the connections, and the reverse EMF caused by the inductance. Where does inductance come from? Any conductors in our system, the traces on the PC boards, the leads of the components, the cabling between the laser diode driver and the laser diode package itself. What can make this worse is, let's assume we have a wide trace or a wide cable, and then we neck it down. That current that's flowing evenly through this nice wide conductor suddenly has to fit into this narrow space, and this is an area of high magnetic field. In other words, we have just created an inductor. Why do I mention this? Because sometimes folks are inclined to use a current probe to look at the output pulse. And a current probe won't fit over a nice big wide flat cable like we should be using, so they may attach a short wire in order to fit the current probe over that. Well, you've just created an inductor. And in fact, anytime you neck down the area of a wide surface, you are creating an inductance. So one of the issues that we have is folks trying homemade remedies that don't involve reducing the inductance, which is really the key here. One of the things that customers will do is they'll take the pulsar. Here's our current source. Here's our laser diode. And they're inclined to connect another diode in reverse parallel to the laser, assuming that we can somehow short out that ringing that takes place. The problem is we tend to forget there's inductance all over the place. The laser diode leads, any parts that we add to the output circuit. You might be inclined to add some resistance out here so that you can draw more current from the pulsar in case the diode is rated much lower than the lowest output of the pulsar. All these things add inductance. The inductance wants the pulse to lengthen. It wants to continue the current by opposing the change, and we end up with current flowing out here, which isn't doing us any good. Here's another thing to consider, and you'll see an example of this later. Our driver sometimes consists of a current source and a switch. The switch is what's actually creating the pulses. We've got a current source, and while the switch is on, we've shorted the current source out, which does not harm it. A current source can drive a short circuit just fine. We have no pulse at this point. When we open the switch, we allow the current to now flow through the laser diode. When we wish to end the pulse, we close the switch. Current now flows in this loop, and it avoids the laser diode, so we have now created a very fast-acting pulse, fast rise time, fast end time. This is sometimes called a shunt or a crowbar. It's actually a transistor, not a mechanical switch. And it's a way of getting very fast pulses. Well, we have inductance, as you know, throughout this wiring. So when we close the switch, the inductance is going to want to keep this current flowing. that can result in a pulse that has a very long tail, and we'll be showing you examples of that later on. In any case, as you can see, the inductance is the bad guy here. Inductance isn't always bad. We depend on it for motors, relays, solenoids, energy storage within the pulsar. But in the case of the output circuit, we want to minimize the inductance. After all, L times di over dt, L is the thing we have control over. We can't reduce the current unless your application allows you to do that. And typically we want very fast timing, so we can't lengthen the pulse. So we can only control the inductance. Let's try to keep that down. So another thing that customers may ask about is impedance matching. They will wonder if perhaps this problem can't be solved by simply put an impedance matching network between the current source and the laser diode. The problem is a current source has a very high output impedance. A laser diode has a very low impedance. It's very difficult to get these things matched, especially at the current levels that we often deal with here. Another possibility is folks are looking for maximum power transfer. Again, that's not our goal. What we want to do is push a lot of current through a load in a very short period of time. So to avoid inductance, what can we do? For one thing, we can keep this connection short. The more cabling you have between the pulsar and the laser diode, the more inductance we're going to have. What else happens? We have adapters, we have connectors, we have clamps, we have alligator clips, all manner of hardware being used between the pulsar and the laser diode. All those things add inductance, and so they should be avoided. The most direct connection is the best. So, how about things that do work? Well, the thing that works the best is the thing that has the widest surface area. We call it strip line. It's not exactly the same thing that RF people use to describe strip line, but in our business it's a symmetrical cable. I've got a large one here. We've got a fairly low inductance connector at the end. We have many contacts in parallel. It's about 1.25 inches wide. It's made out of very heavy copper. And there's actually two conductors here. They're thin. They are kept close together. However, we try to keep this as symmetrical as we possibly can. Why? Because the current going out from the driver to the laser diode on one conductor generates a magnetic field in one direction. The returning current generates a magnetic field in the reverse direction. Those two magnetic fields cancel. If you don't have a magnetic field, you no longer have an inductor. So the better job we do of keeping this cable flat, symmetrical, short, the less inductance we'll have and the fewer of these problems we'll have. That brings up another issue, incidentally. Imagine that we have this nice flat strip line and we make a big loop at the end of it. And we're looking at the strip line from the edge. These are my two conductors. If we make a loop in order to connect it to our laser diode, what have we done? We've just created an inductor, a one-loop inductor. There's something else we have to remember to not do, and that is we don't want to ground either the cathode or the anode of the laser diode. Sometimes the clamp arrangements on the table will do that. They will ground one side or the other, but now you can see what's happening. We're feeding current out to the laser diode through one conductor of the strip line, and it's returning to our laser driver through ground and not through this conductor. Obviously, the current is unbalanced. More current here, less current here. The magnetic fields will not cancel. We've just lost the reason for using strip line. Some folks may be inclined to use other types of cables, twisted pairs, and so on. You can do that if the rise time is not so fast. We have products that use twisted pair as the output cable, but those rise times are in microseconds and not nanoseconds. Big difference, factor of 1,000 there. We have a couple of other examples here of strip line. This is a small, much more flexible strip line that is used with modular or single board type pulsars. It's basically two strips of copper separated by some kind of Kapton or similar insulator, very thin, very flexible. Again, use the minimum amount necessary to do the job. It still has inductance, although not so much. The question often comes up, how do I tie strip line to my laser diode? The laser diode may not look anything like this. It may be in a very unusual package. Well, the best scheme that we've come up with is to recommend making a PC board. PC boards are cheaply made, readily available. You can hack one up by simply taking a two-sided piece of PC board material and a coping saw and cutting it out to match whatever sort of diode you have. You can then solder the strip line to the two sides of the board, nice wide flood solder connection, low inductance, and do anything you want on the other side of the board. Here is a board that has a DE37 on one side, and it's got a ground plane on one side and a power plane on the other side. We can put the laser diode and straddle the board if you wish, soldering one lead to each side. You can put the laser diode in on right angles if you want to by putting a hole in the board and soldering one lead to one side and one to the other. It's an easy way to interface the package of the laser diode to the strip line. So what about measuring the current of a pulse? How can we do that? Well, probably the very best indication of what the pulse looks like is from your detector. Looking at the light from the laser diode will give you a really good idea of what the current pulse looks like, and of course that's the goal anyway, to make a good light pulse. The second best scheme to use is to watch the current flowing to the laser diode. One way of doing it is with something like this. This is an accessory with one of our drivers. It has a low inductance connector that plugs into the pulsar and another low inductance connector that plugs into the strip line. And what it does is it puts a bunch of resistors in parallel. They're in series with the current flow, but the resistors are in parallel with each other. This reduces inductance. And we will get a very slight voltage drop across these resistors, which looks like the pulse. So by connecting our oscilloscope to that and looking at the voltage across those resistors, we get a pretty good representation of what the pulse is. Most pulsars have an output of some sort, a current monitor circuit, in which case this is built in. But that's probably the second best way of looking at the pulse. What we don't necessarily want to do is look at the voltage across the laser diode, because we're looking at a current source, and the current source voltage can vary wildly depending on what the load is. A laser diode has a curve to it, an IV curve. The voltage is going to be kind of squirrely, trying to drive that thing with a constant current. So consequently, a voltage impression is not as important as the current. And I really put current probes at the bottom of the list as accurate ways of looking at the pulse. One of the reasons, as we mentioned before, it's hard to get a current probe around a strip line. So it forces us to use a small round wire, which is an inductor, and messes up our envelope that way. The other issue is most current probes are really not very fast, and probably won't give you an accurate representation of what's going on unless you are hitting this with really deep pockets. Good current probes are very expensive. Okay, so at this point we're going to switch to some real-life photographs of what happens when we do things the right way or the wrong way. And this will bring home the point, why does interconnect matter? In our examples here, we're using a BCX420 laser diode driver. We're going to connect it to a load. It's actually a resist load, a very high power water-cooled load that has very low inductance. We have set the driver to 16 amps of current, and we are going to operate at a frequency of 5 kilohertz, and we're going to generate a pulse width of 5 microseconds. We're going to monitor the output with a 4102 TEC oscilloscope, and we give you these numbers just so you see what it is that we set the experiment up for. Now, we have a huge amount of difference between the various types of cables that we can use to connect the driver to the laser diode. Here are some examples. 16 gauge wire has an inductance of 27 nanohenries per inch. If you go down a little bit, it says 14 gauge wire has a 26 nanohenry inductance per inch. As the gauge of wire goes down, the wire is getting larger and the inductance is dropping, but as you can see, it doesn't drop very much. Middle column, how about twisted pair, used for telephones and many other devices? Well, it's better. Per inch, the inductance is 11.5 nanohenries for 16 gauge, 8.75 nanohenries for 14 gauge. Big improvement over just plain straight wire. How about coax cable? Everybody loves coax cable. It's used because it's shielded, so it must be good for driving laser diodes, right? Well, it's better. 7.5 nanohenries per inch for RG58, which is small diameter coax. 4.9 nanohenries per inch of RG8, slightly larger coax. And let's go ahead with our experiment. In this case, we're going to use twisted pair. The yellow and black wires is 16 gauge. We've got 6 feet of it. We're connecting it between the driver and the load. The load is the blue box at the bottom there. We've soldered the wires to a PC board that we have pushed into the load with the connector. The inductance of that 6 feet of wire is 630 nanohenries. Let's see what the result is. Here we go. A slow rise time of some 900 nanoseconds. The fall time is greater than 6 microseconds, and it's even difficult to see where it falls. We're going from the 10% to the 90% points here. Very, very long fall time. And as you can see, there's ringing taking place at the top of the pulse. As we know, that's due to the combination of inductance and capacitance, causing a little bit of ringing to take place because of the resonance. Okay, how about this? We're going to use strip line. You can see we've opened the end of the strip line a little bit and soldered only 6 inches of wire to the ends of the strip line and brought them over to the load. The inductance of the entire setup, excuse me, is 167 nanohenries, much better than it was before. However, be prepared. We've got round wire in the picture here. Bad idea. Here's our pulse. We've cut the rise time in half. We're at 300 nanoseconds. The fall time is better at 2 microseconds. Not still very good. And a certain amount of ringing taking place on the top. How about coax cable? Here's 6 feet of cable. Inductance 540 nanohenries. Well, that's kind of halfway in between our previous 2 examples. It's still fairly high. What has happened is our rise time has gone to 300 nanoseconds, which is not particularly good. The fall time is extended now. We've got 6 microseconds. This is one of those pulsars that uses a switch in the output circuit to turn off and on the current and short out the laser diode, so it's capable of much, much faster times than this. And you can see some ringing going on, and that's because of the capacitance of the shielded cable interacting with the inductance. So, not good. Here's straight wire. The whole 3 feet of straight wire not twisted together. The inductance is 972 nanohenries, nearly a microhenry of inductance. And let's see what that gives us. Overshoot and a very slow rising edge, 550 nanoseconds of rise time, a 6 microsecond fall time, and an overshoot followed by some kind of grassy looking resonance taking place at the top. So not a good application. In this case, we've taken a voltmeter and put it across the load just to show you one item, and that is, this is a resistor for a load. The current and the voltage ought to be identical. They should both be rectangles. Instead, the voltage looks very squirrely here. We've got an overshoot, some ringing, and a very long tail. The voltage is also quite low. It should be 8 volts by calculation, and it's far less, and the question is why? Well, the voltage is being dropped across the transmission line. It's being dropped across the inductance of the wire and not the load, and we will have a very hard time driving the load this way. Here's the answer, strip line. This particular photograph shows a connector at each end. How about these numbers? A strip line that's 0.32 inches wide comes down to about 10.4 nanohenries per foot, much less than the previous numbers we've had. As we widen the strip line, the numbers go down as you would expect. 6/10 inch strip line has 4.6 nanohenries per foot, not per inch, but per foot. And finally, the wide stuff, we only have 1.65 nanohenries per foot. Nice low inductance. So, here's our setup once again. We've got the oscilloscope on the left, the laser diode driver in the middle, the blue box on the right is our water-cooled load, and you can see that orangish strip line connecting the two devices on the right there. This is the proper way to do it, and behold, there's our pulse. We have a 33 nanosecond rise time and a 128 nanosecond fall time, fairly close to what the pulsar is capable of doing. Very little ringing on the pulse, and this is what we should be enjoying with our setup. So here's a chart that compares these various items side by side. Straight wire is the worst. Twisted pair improves our inductance slightly. Coax is a little bit lower. Strip line with 6 inches of straight wire, well, we've just ruined the whole point in using strip line. This happens all the time, by the way. Many customers, of necessity, will put a piece of round wire at the end of the strip line to adapt it. As we've mentioned before, you are far better off using a piece of printed circuit board and some way of keeping that strip line flat, parallel, and wide all the way to the load. Finally, strip line, 1.6 nanohenries, far better than the other possibilities. The real point here that we wish to make today is this simple formula. The amount of voltage that you get induced through a change in current is proportional to the inductance, proportional to the current, and inversely proportional to the time. Since we really don't want to change di, dt, we probably want that really fast in our applications. What we need to change is L. Let's get the inductance out of the picture. We will not have so much reverse voltage or reverse EMF generated, and it will not affect our waveform.